Temperature maps. In this video we will see in advance the function of the NanoFraser, the temperature maps. So what are the temperature maps? Temperature maps are a functionality that allows us to import another layout on top of the existing layout. Let's say we have layout 0. We import another layout through our geometries folder or any layout that you would like to import, and then this will be applied. Let's say our very famous sine wave. This will be applied on top of an existing layout, and it will determine a temperature map following the grayscale image that we have, or a 2D image that we have. So let's see a practical example on how to use these temperature maps. First of all, I created this arrow. So this is also another layout that you may have already seen in the training videos. This is just a very standard pattern. Maybe we can make it a little bit bigger, say 1.5. We import it. In this case, I'm using a NanoFraser Scholar, so there is no laser option. I'm importing it with the standard pixel size and depth of 25. So we have our layout number 2. Then I go to TSPL. I select layout number 2, and the file that we will import here will be applied on top of this writing field. So on top of this field, which basically is referred, since it has a depth, to the writing forces. So if we use a feedback, the feedback will optimize this field to reach this 25 nanometers depth. Then on top of this field we will apply this temperature maps, which in case we're using a feedback may cause some problems with the feedback, because we keep on changing the temperature of the writer. But in case we don't use the feedback, you will see that we will see this sort of map on top of our design, because we change our temperature. So let's say we want to do this design, and we want to change the temperature between 800 and 1050. So what we have to do is, in case we have different images, different layout, different sizes, we have to resize the temperature map to the target field. Here we can change the temperature. We can also ignore the white pixels in case we have white pixels. And then when we're happy with our temperature map, we import it. So we add it to the target field. So you see that now we have these sort of different temperatures of the writer that are applied when we pattern this field. You can see here the scale for the different temperatures. What fundamentally changed from a normal operation is that when we are patterning without temperature maps, we always use a constant temperature, which we select here. So our work is done. In case we want to do some modification, let's say 1049. Okay, here we want to change the temperature map. We have to just replace the new temperature map in the target field. So here we're done with our importing of the temperature maps. You see that I already tried to pattern the arrow without feedback. So I used 850 Celsius, quite a low temperature, and you see here indeed that we're not removing the material very efficiently. without feedback with a force of 4.6. So this is what you expect if you pattern this design, this layout to the smaller arrow. So we can now make a bigger one. So what we can expect if we pattern without a temperature map with a disabled feedback, a constant force. Let's also set maybe a deeper scan height so that when we apply temperature map, we are sure to read everything correctly. So let's just press play again just to make sure that we have a better understanding of what's going on. But in general, what we should see is a similar arrow because I'm using the same exact writing parameters. Just want to make sure that I didn't write on top of the existing arrow. So yeah, we see our nice pattern. Probably the force is already too high. We can put 3.5 maybe. Okay, yeah. 3.5, 4. Let's say 4. Let's use a constant force of 4 for the temperature map. And you see we have a depth of 25. And we are not using any feedback. So this is what we would expect without temperature map, constant force, no feedback. Now let's apply the temperature map. First of all, how do we do it? Let's move our design here. We have to go to the CLL patterning parameters and we select use temperature map. As soon as we select the temperature map, you see that the temperature is grayed out because we cannot change the temperature anymore. We can select different forces, different forward height, but the temperature is set by the temperature map. So let's start our pattern and see what happens. So you can see that inside the arrow now we have the sine wave because we are using this temperature map. Let's see it again. So outside we also have this temperature map, but we are not really reaching the surface, so we cannot pattern. But inside the arrow we are having this sine wave sine wave map of the temperature. So this turns into a sine wave arrow kind of. So this is I think it's a quite cool topography, and it's quite cool to see, but also to understand the kind of functionality that we are dealing with. A nice use of the temperature map is for patterning on insulating substrates. So the concept behind it is that there is a thermal bending associated to the cantilever being heated up. So when we are heating up the cantilever, then we're able to bend it. So even if we're not able to apply a force on insulating substrate because we cannot apply this voltage difference, we can still bend the cantilever by thermal bending. We can also try to do a small test together, just to kind of give you an idea of this concept. So let's use a temperature map. Maybe we can increase this temperature a little bit more. Say we put it between 1000 and 1250. Okay, and we select layout 2. So we increased the temperature. So by increasing the temperature, we have a larger thermal bending, and we're replacing this field. By using much higher temperature, we expect that if we write the same field, we will write, yes, similarly an arrow, but with much deeper patterning depth. At some point, we will have the thermal bending will be able to also write in the areas where we're not applying a force. So actually, let's increase it even more, 1050 to 1300. Replace it. So now I will decrease the force quite a lot. So I just put 1. And we can start the pattern. But actually before that, I will reduce a little bit the forward height. This is because by reducing the forward height, I am reducing the distance between the tip and the substrate, our surface. So this will make it even easier for the thermal bending to reach the surface. So the entity of the thermal bending is less than that of the bending by applying a force. So putting us closer should allow us to reach the surface. So let's see that even when we're not in applying the force, we're still writing, and we're having a forward height of 225 nanometers. So in theory we should not write, but somehow we write. So if we increase the force, see, let's say we put 2. So you see that we increase the force, we pattern deeper when we have the arrow, but we are still patterning when we are not applying a force. So in this case we are using a silicon substrate, but also from the analysis panel, in the pixel-wise writing forces, you can see that outside the arrow we're definitely not applying any force. So what is allowing us to write? The thermal bending. So you can imagine that this is a quite powerful technique when trying to write on insulating substrate, which is one of the limitations of the nanofraser, because we cannot easily apply the force, so we cannot have a feedback, but still we're able to pattern, and this is a quite nice feature for this specific case. And we will have a video where we will go through a pattern on insulating substrates together.